Hello everybody. Welcome back to Calculus 1 Online at Frederick Community College. In this video, I will discuss one of the most important topics of the class, and that is a derivative of a function. I will be using a Desmos activity that was created by another instructor, so I would like to give credit to that person. The name is Lee Nataro. If you would like to complete this activity, as you watch the video, or maybe after you complete watching the lecture, the link will be provided on our course website. Okay, let's go ahead and get started here. We are given a graph of a quadratic function that is crossed by a secant line. Let me remind you that a secant line is a line that crosses a curve in at least 2 points, and we would like to answer this question: in how many places does the secant line intersect the graph of the parabola? So a fairly straightforward answer here. There are 2 points, so that's what I'm going to enter in my answer field. Okay, let's take a look at the next portion of this activity. Here we see that our secant line has a negative slope as it goes down to the right. Okay. Notice also that it corresponds to the portion of the graph where our parabola, our quadratic function, is decreasing. Okay, so we're asked to drag the large blue point to make a secant with a positive slope. All right, and there are many different ways we could do this. So here's one example, here's another, and you can see that there are infinitely many ways to construct a secant line with a positive slope. So I'm just going to go ahead and pick one. Okay, so here's one of many examples where the secant line has a positive slope. Notice this corresponds to a portion of the graph where our parabola is increasing. Okay, so maybe you can start building this connection between the way the function is acting and the secant line. So now let's take a look at a very specific secant line. So here we have 2 points whose coordinates are given to us. All right, so we have the left point 1, 1, and the right point 1.5, comma 2.25. All right, we would like to compute the slope of the secant line and also discuss what the slope represents. Okay, so how do we compute the slope of the secant line? Well, we know from our previous math class that this is just change in y over change in x, or rise over run. So how do we compute that? So that would be 2.25 minus 1. That's our change in y. And we need to divide this by change in x, which is 1.5 minus 1. So we see that our slope turns out to be 2.5. Okay. What does that slope represent? Okay, or how can we interpret it? This would be the average rate of change of our function f of x, our quadratic, on the interval that we're considering on. So this would be interval what? So we're looking for the x values. Okay, our left point would be 1. Our right point would be 1.5. Okay, so on average, this is how our function is changing on this particular interval. And let's go ahead and try to remember the slope of the secant line, 2.5. We're going to need it to refer to this number on the next portion of the activity. Okay, so now let's take a look at this secant line. Okay, what is similar to this secant line to the previous example? Well, we see that one point is the same. The left point with coordinates 1, 1 is exactly the same. But what we've done, we've changed the right point and we moved it closer to that fixed point 1, 1. Okay, we still have a positive slope for the secant line, but how is it different? So what is the slope of the secant line? And we're going to compare our answer to the previous example. So same idea. The slope of this secant line is computed by change in y. So that would be 1.21 minus 1. That's change in y, divide by change in x, which is 1.1 minus 1, and we get a different answer, 2.1. So that's the slope of this line. It is not as steep as the one on the previous example. Okay, let's go ahead and compare them. What does it mean to compare? Well, let's see which one is bigger, right? So 2.1 is certainly smaller than 2.5. Okay, that is our comparison. So looks like as we moved the right point, okay, closer to 1, 1, the slope of the secant line got closer to 2. Okay, that's our educated guess. All right, so that is your comparison here. And now let's take a look at the next portion where we can do this for many, many different secant lines. And we would like to investigate the limit behavior, right? What happens in the limit as we move this point right here closer to our fixed point. Okay, what happens to the slope of the secant line? You see all these different changes, and we get closer and closer to 2. Okay, does it matter from which side we approach the red point? Well, let's go from the left side. Notice here, we're approaching 2 from a different side, but we are still getting closer and closer to 2. Okay, so what is happening in the limit? Okay, the slopes get closer to 2. Okay, does it matter from which side? No. From either side, we are approaching 2. Okay, that is the slope of our secant line. Okay, it's approaching 2 from either direction. All right, so take a pause here, think about what we've done, and now we're going to take this idea and formalize it. That is, give it a definition, notation, and explain what it is that we just observed. Okay, so what we've just done is discovering the fundamental idea of a derivative. Okay, the slope of the tangent line. Okay, tangent line, not secant. Tangent line, that is the line that crosses our function, okay, the graph of our function at exactly that one point. Okay, that's what happens in the limit as we move that point, that movable point over here closer and closer to our fixed point. So we get a tangent line, and the slope of the tangent line is the instantaneous rate of change. Okay, how is our function changing instantaneously at that particular point? And that is also called the derivative of our function. Okay, so the notation for our derivative would be f prime of a. This says take the derivative of your function and evaluate it at a. Okay, and now we're going to discover these different notations for computing the derivative using a limit definition. So let's take a look at the very first option here. It says f prime of a is equal to the limit as b goes to a of this quotient f of b minus f of a divided by b minus a. What does that mean? Well, let's take a look at all of this notation. What is f of b? Okay, that would be the y coordinate of this point that I'm moving, right? And what is f of a? That's the fixed value right here. Okay, so as I move this point closer and closer to my fixed point, then that difference becomes smaller and smaller, right? Okay, so that is my change in y. What about the difference b minus a? Well, that's just the difference, the change in x, okay? That is our run. And as I move closer and closer to the point that's fixed, this difference, b minus a, gets closer and closer to 0, okay? And that is what we mean by the behavior of this particular function as we approach that fixed value, okay? It's the limit, right? The limit of this particular quotient will give us the slope of the tangent line. So we're going to go ahead and check this. Okay, let's take a look at the second definition. Here, it looks slightly different, but really it is exactly the same idea. Okay, it says f prime of a is equal to the limit as h goes to 0 now, and the quotient is f of a plus h minus f of a over h. What does that mean? Well, this is just saying, okay, let's not look at the point with coordinates b, f of b, but rather let's take a look at the change that it takes to go from a to b, right? H really just represents the difference, okay? And it is marked here on the graph. H is the difference between A and B. And as that difference gets closer and closer to 0, this is equivalent of saying, yeah, let's go ahead and shrink that little triangle or get closer to our fixed point, okay? As this gets closer and closer to 0, our line gets closer and closer to the tangent line, so that is giving us the derivative of our function at that point. Okay, we're going to go ahead and check this one right here. These two are equivalent limit definitions of a derivative. Okay, and the last one is just the notation and the interpretation of the derivative. F prime of a represents the slope of the tangent line to the function y is equal to f of x at x is equal to 0. Okay, that's just pulling it all together. Yes, we're going to say yes to this. Okay, so now I would like for you to take a moment, pause, and really think about what we've just done. Look at these definitions, let it kind of sink in. Okay, because this might be the very first time you encounter something so formal, okay, a little bit abstract, right? You might be still confused about what is that h? What do you mean by f of b minus f of a? Okay, really all this is just a formal definition of a slope, okay, and how it behaves in the limit. All right, so I'm going to go ahead and pause, stop this video right here, and we're going to split up this lesson into portions. So in the next part of the video, we're going to do computations. That is, we're going to apply these formulas and compute our derivatives. Thank you for watching.